Well, welcome everybody. Good morning, good afternoon, good night, perhaps, depending on where you are. Well, it's really a pleasure for me being here, giving the first talk of this season for the webinars of this project, Accelnet Multinet, and just as being part of one of the committees. And I guess that nowadays, when we are talking about multiplex networks, for all of you are already familiar with this concept. And for the multiplex, basically what we understand, just to make the distinction with respect to multi-layer networks, is that for a multiplex, we have exactly the same set of nodes in different layers. We can have different connections, of course, and then what we have is just a one-to-one correspondence between nodes at every single layer. This can, let's say, represent the structure of some social networks, for instance, how people communicate according to different channels. Well, here there is some application that I found that you can run in your computer, perhaps you can run even in your cell phone. And this is a pretty, let's say, amazing on some hands, but it's also a little bit scary, because this means that you are giving access on these different messaging systems to a single application, which is giving control over your different, let's say, channels of communication with your family, with your colleagues at work, depending on the type of connection that you are having. And then here, this is just an example on how we identify in every one of these channels of communication, we are the same user along all these channels, and then that we can establish different links of connectivity. And then this can represent also different ways of communicating with our family, with our friends, with our colleagues at work, and so many different ways. Okay, and of course, for the multiplex, one of the examples that we have seen in these years that it's also quite common. It's apart from these social networks, is also the problems related to transportation, in which we can have different airlines, and then how these different airlines cover different parts of different sets of airports, or we can have here in a country how we can have different sorts of transportation media, and then how this transportation media move between different places. You have here another map which relates again to transportation, which is it can identify as the difference between the patterns of connectivity between the different companies. Here we have Iberia and Vueling, which are two Spain-based companies. And then you can see here, so here we have numbers which are the kind of a distance between networks. So Iberia and Vueling are very, very close. But for instance, with Ryanair, we get the larger distance with respect to Vueling. And then because, of course, that the patterns of connectivity that they follow are very different. So this is another example on which are the types of construction that we can have in mind when talking about multiplex networks. But you know that even in the case of time-dependent networks can be seen as a multiplex network, because here again the nodes are a kind of a replica at different time steps, and then we, of course, the nodes have some sort of causality connection, we can say, in this a long time. Well, in my talk, I will focus on the different types of dynamics that let's say we have been working in this the last days, basically in our group, and how this can be seen in a let's say in a formal way. So basically, we have been working from the most basic interaction, which is a linear system, in which we only have basically diffusion, and then we have introduced different types of nonlinear interactions, giving rise to different phenomenology that I will describe along the next slides. Well, let me put the first slide on basically on the idea of what does this kind of a conceptualization of the dynamics in a multiplex network. So basically, what we have is something not so different from what we have in a simple network, in which basically what we look is at the state of some variable, which is it's a vector that it characterizes the state of the different nodes at different layers. That's the reason for which we put this vector in the sense, and it depends on the state of the system of in some complex way, and depends on topologically on the state of the connectivity, which is this M that we put here, which is a kind of generalization of the adjacency matrix. So we will see later how we should precisely write this general adjacency matrix. For instance, and the state of the variable is just a kind of dynamic feature of the model at the different layers, for instance, which can be the number of passengers waiting for some transportation system. Well, in particular for a multiplex, actually what we have is this matrix, which is a kind of a 4 indices object, in which we can specify that when alpha is equal to beta in the top indices that correspond to the layers. So when alpha is equal to beta, we think that it corresponds to the adjacency matrix of a singular layer. When I is equal to j, it corresponds to how the node I is connected to the node I in other layers. So then we could say it's an inter-layer connectivity. Of course, and then when we have I different from j and alpha different from beta, then this matrix elements are 0. So then we can write formally the time evolution of the system in this way. I corresponds to the nodes, alpha corresponds to the different layers, and then we can write explicitly the dependence on this. So it depends on the states, it depends on the connectivities through this aij alpha through the connectivities in the same layer, and then mii alpha beta to the connectivities across the layers. So basically what we used to have is that these elements I alpha beta don't depend on the particular nodes, and they can be 0 or 1 for all I, and then it means whether two layers are connected or not. So we don't expect the connections to be different from node to node, but we expect that this is a property of the layers, not of the nodes. So here in this case, where we have two particular cases, we have 3 layers, and then on the left, what we have is that this layer, layers 1 is connected to 2, 2 is connected to 3. But then on the right case, what we have is that furthermore, 1 is connected to 3. So you see here the layers are the same, but the connectivity matrix between the layers is different. So we have to take into account all these different constructions. So let's go now in the particular implementation of the most simple models, which is these models related to diffusion. So diffusion is usually the starting point for physicists to start the description of, let's say, well, a system. I wouldn't say complex. So it starts to be complex because of the topology, but not because of the dynamics. And then we will see how we can make different steps and looking for more complex dynamics. Well, in this case, it's very easy. So basically what we have is diffusion in the layers and also diffusion across the layers. So this was a model that we introduced some time ago. And here on the left, here you see on the top, you see the label for the layer. So it means that on this left sum you have is diffusion inside the layer, and then this term on the right, then what you have is dKl is the diffusion coefficient across the layers, and then what we expect is that we have only diffusion between node I at layer L and node I at layer K. That's because we were saying before that we only have this type of connectivity in order when we talk about multiplex nodes. Well, basically the idea when we were dealing with these linear models is that now instead of looking at the system in this 4-rank object more complex, I say basically the idea is to make a kind of unfolding this information and then put this information in terms of what has been called the supra-adjacency matrix or the supra-Laplacian matrix. Then basically what we think, this is for the case of 2 layers, what we have in this construction, what we have in this term in the left corresponds to the Laplacian matrix for the single layers L1 and L2. So this is basically n by n box in this matrix. L2 is another n by n box. And here on the right, what we have is dx. Dx corresponds to the diffusion coefficient across the layers. And then what we have here is the identity matrix here in 4 boxes. And then in the diagonal boxes, what we have is the identity matrix because it corresponds to a pure linear interaction, linear diffusion across the layers. And then we have minus I in the, let's say, in the, not in the main diagonal. And then because this is related to the fact that the Laplacian is represents a conserved quantity. Then what we have here is we have a kind of representation in which all the information for this system is contained in the supra-Laplacian matrix. So it's an object of a 2-dimensional object, it's a matrix, and then in this matrix, what we can make is analysis of the eigenvalues and eigenvectors as usual. And then, but the point now is that how we can relate these eigenvalues in one case or the other. But before going into this, let me remind you that why are the eigenvalues important in the description of diffusion in a matrix? Because here you have an example, very simple example, which here you have this equation, which is an equation of which you have the Laplacian, so it's a linear set of differential equations, and then you can write this set of differential equations in terms of the normal modes. So this is very typical algebraic procedure. So you can write in terms of this, and then you can take this set of equations, and then you can just play a little bit with them, and then look at which is the difference at any time, and then you can make a kind of average on initial conditions, and then basically what you get is according to the properties of the average that you have initially, and that then basically what you can write at the end is that the difference in the values of these quantities at time t decay as a sum of these different contributions. These ULM are the projections of the eigenvectors on the eigenmodes, and then square this is the difference between L and K vectors that we have, the original variables here on the left. And then with this in exponential decay, of course, we have a linear system and the decay is exponential. And then this exponential decay is in terms of the eigenvalues of the Laplacian matrix. So what we can say is that this system will approach a homogeneous state exponentially in time. And of course, here what is important is the smallest eigenvalue, because the smallest eigenvalue is the one that is giving you how the approach to the homogeneous final state is produced. Also, this expression is also the reason for which some of the let's say methods for identifying communities and to see are based on the projections on the Laplacian of the eigenvectors of the Laplacian matrix. Well, here in this case, we were making these different types of constructions between the layers, but one of the basic things is that depending on the structure of the layers, we get something that we're calling super diffusion, in the sense that now coupling these 2 layers, we can get a diffusion, so we can get a second smallest eigenvalue, this lambda 2, which is larger than any of the 2 eigenvalues, the smaller eigenvalues of the separate layers. So this is, we call this rise to this that we call super diffusion, and then you get here in this picture a comparison between these different behaviors. Okay, but this is just the most simple case. So we have this linearity, but okay, linear is simple, and then we are usually interested in nonlinear systems. Here I put is even if you have diffusion. So diffusion, depending on the quantities that you are taking into account, it can give rise even to nonlinear model. But okay, let's try to make a classification now that we are assuming that we will have a nonlinear behaviors, and in sense that which are the different dynamics that we can play in we can make in this game of dynamical properties of a multiplex network. Well, this is clear. So we can have we have layers, and then we have layers, and then we have connections between the layers. Of course, one case is that we have the same type of dynamics in the layers and across the layers, and this was the case, for instance, of diffusion, because when we talk about diffusion, we don't distinguish between the physical, let's say, the physical modeling, so the physical interpretation of the dynamics here, and then we have diffusion on the layers, and then we also have diffusion across the layers. But we can have these connections can represent different types of interactions. Then, for instance, that we have the same intra-layer for all the layers, but then we can have different physical meaning between the layers. So this is with the problem related that we'll see later. This relates reaction and diffusion. So we can have different intra-layers dynamics and interlayer. This is the case of synchronization, as you will see later. And for instance, you can also have you can also deal with the topic which unfortunately it's so hot so hot in the last couple of years of this of spreading, and then you will see also some of the examples about the spreading that are related to these dynamical properties of multiplex networks. And finally, we'll show you some cases in which you don't even have connections between the layers, but that you can identify some causality properties between nodes in layers that can also be interpreted in terms of multiplex. Well, apart from the pure linear case, which is the most simple, here I introduce a problem in which we were working some time ago, which is the problem of reaction and diffusion. In this case, what we were taking into account in this setting is that we have diffusion on the layers, but then across the layers, we are taking into account that the populations here, this can be to activator or inhibitor, corresponds also to some prey-predator models. Here, what you can imagine is that even if we put these two layers separately, actually, what happens is that in the nodes that corresponds to two different types of populations, what we have is reaction. So the preys and the predators are reacting. So they are changing. They are making changes in their populations, and then whenever you have an activator or an inhibitor, something happens. So there is some sort of reaction, any type of function that you can imagine that you have here. But what is important is that on the layer, you have purely diffusion. What we found in this case is that because of this multiplex construction, and depending on the relations between the degrees of the nodes in one layer or in the other layer, a construction of a system in which, in principle, you don't expect to have instability, then it develops the instability. So this gives rise to very similar to this pattern formation. In this, and these patterns appear in the layers, and it is because of the multiplex construction. It is because we have, as I was saying, so different types of behavior, different reactions, and different diffusions in the two layers, and this is the reason for this to appear. For instance, we were also working in a model of a language competition, or a model in opinion dynamics competition. Here, the setting is very simple as well. So here, what you have is basically a layer of social interactions in which what you do is you speak language with other people, and then you decide which is the language that you use. And then in the other layer, you are the same user, but then being the same user, you have a one-to-one connection to the other layer, but then you have a different set of connections. So this can represent a family in one layer, and the other can represent professional interactions. And then you can decide to use a different language in one type of interactions and the other. Then this is the reason for which we also put different colors in the different layers. And this gamma is a kind of, let's say, inertia parameter, which makes you feel very comfortable with the language in one layer or the other, and then you are very reluctant to change it. So then you can make this type of a construction, and then what you define is which is the probability to change the language that we are using according to some parameters, which I will not enter into details. But here what we get is the basic conclusion is that the outcome is quite, let's say, favorable to avoid the consensus, because then in this case, when you talk about the languages, getting consensus is not so good, because when you get the consensus means that one of the languages disappear, and then basically, so for these of us that live in a bilingual or trilingual world, so we are very happy, and then we are even very proud of this coexistence of language. And then I think that this type of modeling in which there is some survival of the languages can be also quite useful and to take into account even from this. Well, let's talk now, as I was saying, in this unfortunately so hot topic in the last couple of years, well, more than 2 years now. And then this of the disease spreading, of course, mainly related to COVID and all these consequences. So what is here, which can be the type of construction that takes into account the multiplex structure? Well, you will see here that we can think on different interaction networks, that we can take into account also how the information is spread, how the virus, how virus can be spread. And then here I will show you is just a couple of words. There are many words that take account into this. This is one contribution that we did last year, in which what we wanted was to design strategies for a useful network partition. Of course, the best strategy is the lockdown, stay home, and then don't interact with anybody else. But then here our point is that basically we have two types of interaction, and eventually we can introduce a third one, which is the social. But basically what we have is two types of interaction. One that represents work, and then what we have is different companies, businesses, or things like this. And then in the other layer, what we have is a home. So we have families, we have the groups of people living together. Of course, we have different patterns of constructing, of people working together and people living together. Then depends on, of course, on different societies. But then here, the interesting point is that you can construct these layers according to different rules. And then, of course, what happens along the day is that all these networks collapse. And then even if they form disconnected, they don't form a connected component here on any of the two, then when you look at the merge network, then you see that they really make a connected component. Here, the idea was that taking this into account, how people live, how people work, that we could define some sort of a strategy, let's say, avoiding just some people not working, and then, let's say, having, in this case, avoiding the appearance of a single connected component, which of course favors the propagation of the disease. So then if you are able to look at some precise important links that are shared between different layers, and then this can make a strategy that can be better for this. So we introduced this, and then we're proposing different strategies for constructing based on this property. Of course, this also was also used by some of the groups also here in this project. In particular, it's very interesting, this work by Alberta Leta and all the people here in the group in Boston, and so many other people. And here you see that this very similar construction that you have. Basically, you have the different layers. In this case, they were working with real data. In the school layers, you have the workplace and community layer and the household layer. Then you have different constructions, and here again, so the nodes are the same. The nodes are the same users, and then along the day, you are interacting in one way in one layer, in a different way in the other layer. So then it makes sense, and then you can look at this construction again, and it makes sense, different types of predictions that you can make. So then it also came to my mind, it's this very nice work by Clara, Sergio, and Alex, that Clara was talking about already a few a few months ago, which is clearly here is again. So it's how the disease can spread physically because we have physical contact with the others, but at the same time how the information about the awareness of the disease propagates between the users. And of course, this doesn't need a physical substrate. It's just you can call this as a virtual contact, and then just playing with this you see you are forming this case again. It's two layers. This is clearly a multiplex construction because you have the same users in the two layers, but the interaction is according to different type of dynamics. Even let's say it's the same, so there is something spreading information in one case, awareness, and physical disease in the other. And then just to end, let me talk a little bit about this let's say this phenomena of synchronization. This phenomena in let's say in the modeling that has been used in terms of multiplex networks is very important because it's crucial in the description of neural systems, in particular in the brain, because actually this phenomena of synchronization has been associated to some type of epileptical seizures. Of course, again, I'm not trying to give a complete overview of all the works that have been done that you can find in different review papers that have been already published in these years. But just as a matter of fact, remember that we were at the beginning when we were talking about linear properties and linear models and spectral properties of the eigenvalues. In this case, when we talk about synchronization, some of the works are related to the stability, to what is called the master stability function. And then the theory that is related to the master stability function is based in showing how is the stability of the synchronized manifold. And then the stability of the synchronized manifold is related to what is called the eigenratio, which is the ratio between the second smallest eigenvalue, lambda 2, and the largest eigenvalue, lambda n. And then what we show here in this paper is that there is a value in between when for the interlayer coupling that optimizes the response of the system, in this case about this stability of the synchronized manifold. Well, we were also looking in this direction to a very well-known case, which is this of the C. elegans nervous system. In this case, we were also considering this multiplex in the sense because in the C. elegans nervous systems, one can identify very clearly the topological communities in the system. And then what we were considering is to different types of interaction. One is electrical and the other is chemical, and different between, and one layer considers one type of connection. I don't remember now the details, one type of connection within the communities here on the bottom, and the other, the connections are among nodes across different communities. So again, this is a multiplex. In the two layers now, what we have are the same nodes, and then they have different sets of connections, and then we have again a one-to-one correspondence. And in this case, what we were obtaining is a particular response of this system in terms that, depending on the parameters, we are obtaining from a coherent behavior to an incoherent behavior in all the communities separately, and finally to some sort of chimera behavior, because we were obtaining, on one hand, some of the communities were perfectly synchronized, and the other were having a kind of partially incoherent dynamics. So, and then it's very clear that these two type of dynamics can coexist in this type of system. And just to end this presentation, let me talk a little bit about something that perhaps you don't expect, as I was saying at the beginning. So now what I have, this can be the case of the, well, to say the brain is very, let's say, and what I would say is that there is a relation between when you make measures in the brain or in people talking about usually about the structural connectivity, which are how are the real connections in the brain made, how the different parts in the brain are connected. But then at the same time, it is also important to talk about functionality. So this functionality means, again, that they have a network, and what they measure is how different parts of the brain are connected functionally. It doesn't mean that now there exists a real connection, real wired connection among these different parts of the brain, but that there is a, we could say, a kind of a correlation, in the sense that there can be two parts of the brain that can be activated simultaneously, giving rise to some sort of a local partial synchronization. Well, in order to analyze this, in this case, this behavior, we introduced some time ago a model which is very similar to a very well-known model as the Kuramoto model, that probably most of you have already known. And here the only point is that we introduce this parameter alpha here, which is called the frustration parameter, and this parameter is responsible because here you see that we have exactly the same frequency for all the oscillators. Then this frequency, this frustration parameter makes that now the synchronized state is not an attractor of the dynamics anymore. So this means that now we will have some structures, some patterns of a phase difference between the nodes in a network. And this is what really happens. So here we have some very simple cases, and then you see here these nodes 7 and 4, these nodes 2 and 3, these nodes 6 and 7, or in this construction, which reminds you probably of the Bethe lattice, you see here the colors stand for nodes that have the same phase in the stationary state. Well, here it means that we have nodes, for instance, nodes 7 and 4 here, that are synchronized even if they are not in direct contact. That's the reason for which here we were calling this remote synchronization. So then it means that two nodes that are far apart in a network, now because of this particular type of interaction in a functional sense, they can be connected. And actually, this is what we observe when running simulations of this type of Kuramoto model on a real connectivity matrix in the brain, and then observe that these two parts of the brain, this blue and the green one here, you see they are very closely to be synchronized. So you have this behavior here, and then they are very likely to be synchronized. But the red and the blue, which are very close, are not so much synchronized. So then it means that here in this construction, the blue and the green areas of the brain are synchronized. In our functional interpretation of this, we can say that they are functionally connected because they're, according to some activation of the brain, their, let's say, their dynamics are well synchronized. Well, this opened some work that we were following in our group. Actually, this was the result of the thesis of Gemma Roussel Tarragó, and we were analyzing very carefully the roles of symmetries, and then with this translation from the structural to the functional, and even at the end, in the final paper, we were proposing a kind of a construction of what we were calling a dual network, in the sense that we have a network like this, and then of course you can identify how this network has some sets of nodes that are symmetric, and then what we introduce is a procedure to identify symmetries or quasi-symmetries in a network according to their response to this type of Kuramoto model with some frustration parameter. Then this enables us to construct networks in which the connections are between nodes which are symmetric, and this can be generalized to any structure. And then even at the end, to make up a network that we call the dual network, in the sense that this network has links between nodes according to the dynamical response. And then in the case here, so you see different colors, not corresponds to local dynamics here, but corresponds to local symmetries in this network, how they are here in this picture, how they are now, let's say, part of the same functional network. Okay, that's it. Just to close my presentation, multiplex networks are here. So we are part of a community, and then of course we are recognizing which is the importance of this type of constructions. And of course, they are suitable models of interaction. So we can use this as a paradigmatic models for constructing, for representing different types of dynamics in nature and in society. Of course, you can think on very different types of interaction. I have just shown some of them. And we have, at the end, we even have some new features that we can say, so it's a part kind of emergence of this new construction, which somehow is the paradigmatic message that we many times give about the complex systems in which, okay, the sum is so the sum is more than the linear combination of the parts. So we have something else. Here we have something else as well, that we don't have just two different sort of dynamics, but we have some sort of more complex dynamical response. Well, and of course, at the end, I would like to thank the funders for providing funds for all these projects that we have taken in these years. And also there is a very long list of collaborators that just not to forget any of them. I didn't write it here, but of course I have in mind most of them. And also thank to you for your patience and for being here. And well, now I am ready if you want to make some questions. Thank you very much.